Hello, everyone. Good morning, good afternoon, good evening, depending on whichever part of the world you are joining us from. Thanks for joining and thanks for taking part in the second last meetup of the year by Kaggle Days Meetup Delhi NCR. This is our 41st meetup where we are glad to host Siddharth Samant. He would be talking around the topic of quantum computing, machine learning, and the challenges in conversational AI. And I think this is one of the topic which has been in craze and would be a great close to the year that we are heading towards. So over to Siddharth. Like you can start sharing a screen and then a short
Sure.
intro before we start. Yeah, it's visible now.
Hey everyone, good evening, good afternoon. Thanks for joining. So, I'm Siddharth. I've been invited to take a session on quantum computing and challenges in conversational AI. So, basically, I'm based out of Deloitte. I've been in Deloitte for the last 1 year. And prior to that, I was in multiple startups. So, I have a lot of experience in taking sessions, making sessions for people, interacting with people on AI. And my work is majorly based on conversational AI. So basically, whatever the client requires, be it classification tasks, be it text generation. So I am particularly involved with understanding what problems the client is facing and then accordingly suggesting what solutions we are having. Now, we decided that we will make this session an amalgamation of quantum computing. And once we are done with that, we will try to link up that how quantum computing can help with the latest AI challenges. And then we will deep down, we'll go to discuss about conversational AI and particularly the problems of conversational AI. So, what I want to reiterate is that this session is not a session where I would start with some words, do some data pre-processing, and then I'll try to run some model.fit and model.prediction. What I'll do is I'll talk from the experience that I have in putting models in production. So I'd like to differentiate the academic aspect from the ones which we face in our daily practical lives. Now, a lot of things, the questions that arise once the model is in production, the costs involved, and how we realize that once we are trying to put models in production, that not everything can be understood just via mathematical costs functions and equations. So before we start, like I said, let's try to fit in some an agenda of the session. Now, how we will traverse to the entire through the entire 1 hour. So we will be starting by understanding quantum. So I'll draw a lot of analogies with AI because I remember like when I was in high school and 5 6 years back, uh, AI was a word, a buzzword for a lot of us, and I'm pretty sure that none of us knew about recommendation systems back then when I was in high school. So quantum is something on the same lines. Currently, if you ask someone that have you heard about quantum computing, the first thing that comes up is a sense of mystery, is a sense of like uh, bizarre word that comes up that okay, I have idea of what quantum mechanics is, but I've never seen how a computer works out of that. So similarly, on the same lines, AI was 5 6 years back. Obviously the tech giants were using it, but the usage was minimal, at least from the sub organizations that use these products as services, right? So if today you find an organization that is using some AI service on AWS, probably that wasn't in usage 10 years back. Now we will try to understand in the first segment of the session that why the very need of quantum computing, like why the very need of AI was there. And once we are done with that, we will try to look at few problems on a very high level, and then I'll try to talk about one of the problems in some detail, obviously as time allows. Once we are done with that, I will try to link up the quantum computing genre with machine learning and why we are saying that uh, eventually quantum computing can help a lot in machine learning. Then once we are done with that, we will talk about few resources that you can access for that if you're interested, and if I'm successful, then I think I hope that I'm able to put you in a situation where intrigued by quantum computing. Once we are done with that, we will go to conversational AI and we will talk about the challenges that we face in production. So with this, let's get started. So to understand why do we need quantum computing? We need to understand and we need to feel the importance of why the what would happen if we don't have quantum computing, or what are the subgenre of problems where quantum computing can help us. For that, we need to understand the limitations of a classical computer. Now, everything was going great, right? You have your laptop, you have a system, you can access cloud resources. What was the very need of something as bizarre as quantum computer? What are the subset of problems where quantum computer is there to solve? Now, right off the bat, I'd like to clear two things about quantum computing. The first one is quantum computers are not some advanced version of your classical computers. So it's not that some very intelligent guy came up and told, hey, I am rewiring the operating system, or I'm using some sort of new binary search or whatever XYZ algorithm that I'm having. I'm introducing some new variables and voila, you have your quantum computer. This is not the case. Quantum computer is a completely different paradigm. It's nothing like some upgradation of your classical computers. Second thing that I'd like to talk about quantum computers is that quantum computer is not here to replace classical computers. And there is a very beautiful comparison we'll draw later. I mean, a lot of people I know are into gaming. Personally, I'm not there, but we know how graphical processing units are there today, present today, and how they help us to enjoy all these video streaming and gaming services, right? I'm not talking about from a coding perspective and deep learning perspective, but I'm saying that these graphic processing units, so called a different way of computing, are there to support what classical computers does. Similarly, there is a very brief and finite genre of problems where quantum computing is there to help, and in no way computer is there to replace what classical computers do for us. So with these two very crucial information, understanding that quantum computers are not there to replace, and that they are a completely different paradigm and nothing that came out from a classical computer, let's try to decode one of the problems where it's really difficult for a classical computer to solve. Now, I'm pretty sure during your college days, you might have studied some algorithms, be it searching algorithms, be it sorting algorithms. And during that time, you might have encountered a concept called time complexity and space complexity. So now we will focus only about time complexity. Now, we have problems that increase in time complexity linearly. Similarly, we have problems which increase in polynomial succession. And similarly, we have that increase in exponential succession. So we are aware, and I'm pretty sure that we have a general understanding of what time complexity is of algorithms. So with that, let's try to look at one of the problems which varies exponentially, and that is the encryption problem. So if you're not aware of RSA, RSA is just an encryption algorithm. It's a 617-bit encryption algorithm, and RSA is nothing. It just stands for the initials of the scientists who developed the algorithm. Now, these algorithms that protect the so-called security of your internet, a lot of banking applications are based on RSA encryption. These applications rely on the fact that it's very difficult to factorize large prime numbers. Now, I'm going to repeat this line. It's very difficult to factorize large prime numbers. Now, you'd say that how do you define very difficult? Now, I'll counter with a question that how do you define NP hard and NP complete problems, and how do you differentiate them with the P ones? So, a lot of logic is based on this factor that it's very difficult to factorize, uh, find the prime factorization of that. Now, I have taken this text information that's present right in front of you from IBM Qiskit. So, IBM is one of the leaders in quantum computing, and Qiskit is the application, basically the coding language that we use to program quantum computers. So, this is an example that I'd like to show you so that you can appreciate that why quantum computers would be useful, are useful, and once the hardware is well enough, it can eventually break theoretically the RSA algorithm. So let's imagine that you have a pin which is of 10 digits or 10 bits, right? And let's assume that your classical computer, as of now, in today's age, one of the best classical computers that you have, can perform 5 into 10 to the power 9. Okay, 5 into 10 to the power 9 combinations per second. So what you're trying to do is solve for a digit the exact combination which will break the encryption. And I'm talking about a computer that is as efficient as a 5 into 10 to the power 9 combinations per second. Now, as I said, that there are certain problems that increase exponentially. Now, if I increase the number of digits in the pin from 10, just a mere 20, just to a mere 20, you see that the computer that was taking 1 second to solve, now it's going to take close to 150 years in terms of human years and time to solve the same equation, the same problem of breaking the encryption. And RSA is based on 617 digits. So you can imagine that what time, like it may cross the age of the universe to break an encryption that big. Now imagine 2000 bits and 3000 bits in place. So you see, I think using this particular information and this particular problem statement, I hope that I have made it clear that there are a few problems that are far away from the reach of classical computers. And there are few problems like traveling salesman problem, right? Which we solve. Now, the first question that might come up is, okay, you're saying that there are certain problems which cannot be solved uh, classically. So, how do you solve them right now? Are we completely ignoring them since we don't have quantum computers? The answer to that is we are being satisfied by local minimas and optimas, yeah, maximas in those solutions. We are having a greedy approach. We know that it's not something that's solvable for the next like couple of years, a couple of thousands of years, some problems, but we are satisfying ourselves with the fact that we are getting to a local minima or maxima as the problem sustains. So now let's talk about applications. Now, as I said, that the first thing that should come to your mind while learning quantum mechanics, quantum computing, is that we are looking for problems, the exact subgenre of problems where we have a lot of permutations and combinations that we can solve. So this is a slide from one of the sessions that AWS itself took. So we had a meeting where this was a session by AWS. So I just took a screen grab of that. So AWS has a service known as AWS Bracket, where it's providing you with all the solutions where you can try up notebooks, you can try different solutions. But right now, I want you to focus on all these individual sectors. Now, I'm pretty sure that all you people have some background in data science, machine learning, or deep learning, AI, and all that stuff. So can you imagine that what sort of permutation problems, let's say we are talking about the logistics sector, right, in front of your screen, what are the terms and conditions that we need to optimize and what are the problems that we might need to optimize? Now you might say that, and you might say correctly that, okay, let's say we have a lot of shipments. So I'll be talking about one of the use cases that Johnson & Johnson, the famous cosmetic industry company, solved. So what they had was they have packages of different sizes, right? And they have these containers which you can see in the image that they need to ship. Now a very important problem to optimize is that they have shipments through trucks, they have shipments through airplane bins, they have shipments through these containers that are shipped through these seaports. Now, the problem statement was, how do I optimize the bin space with the packaging shapes that I have? So every package that you have might be having some length, breadth, and height. And what the problem statement was that, can in some way using quantum computing, can I optimize that problem? Similarly, in finance, one of the most famous and classical use cases is portfolio selection. So, if somebody out there does a lot of trading and is involved in a lot of financial service, investment banking services, they might be knowing the term portfolio selection and risk management. So basically, you have a set of options that you have, options and trading options that you have, and you need to make a portfolio out of it so that your risks follow a certain constraint and you want to optimize your profits, as simple as that. So that is one of the cases that quantum computing has showed a lot of promise. Again, if you try to solve it classically, there's one of the banks out there known as Bank of Spain. So what they did was they partnered with one of the cloud configuration providers, D-Wave, which we will look at in the next couple of slides, and they solved the problem of portfolio management, which would have otherwise taken thousands and thousands of years. Similarly, we are talking about agriculture, pharma, energy sector. So pharma sector, you have drug discovery. Again, a procedure where you have to do a lot of experiments before you come up to a stable version of the drug. So these are the basic sectors where quantum computing are helping. And obviously, I'm not talking about machine learning because eventually I'll be talking about that in a separate dedicated slide. So I have talked about why do we need it. I have talked about what are the sectors where they are important, but I have skipped the question till now, as in what is a quantum computer. Now, I've already in the first couple of minutes I told that the first thing that we need to understand is it's not just some advancement of a classical computer. So let's try to understand that what is this bizarre name known as quantum computing. Now imagine, try to remember your childhood where you used to play with all these bubble sticks, where you used to sway around the bubbles, and accordingly the bubble used to take different interesting and comical shapes. Now I'd like to rephrase and I want to re-emphasize one point over there, that during your high school years, you might have studied that whatever bubble we are talking about, the surface is built in a way that the surface tension is minimized, right? So there is an equation out there which represents surface tension. And somehow, a very cute little stick, a bubble stick, is doing that effortlessly. Now, if you try to simulate this bubble problem on a software, and which is I think one of the classical examples of this is an architectural problem where the architects were trying to solve a problem where they needed to optimize the material that they were using for building arches. And it turns out that it's very similar to the problem of how a bubble would reconfigure itself if it's getting the same bubble stick orientation as compared to the physical arch conditions of the building. Now you see something that would be very complicated to simulate in your so-called classical computer using logical gates and all the programming stuff. A really small bubble out there, really small water bubble out there does that so effortlessly. And all this because physical systems are known to exist in the least possible potential energy configuration, right? So if I tell you that if I can translate business problems to something as simple or as common as a bubble, and I can say that I am sure that whatever configuration I'm transferring to this bubble, I know that the solution that this bubble will provide me will consist of the minimum surface energy, and hence the configuration will give me a global minima. So you see what abstraction I'm trying to put over here. And to re-emphasize this thing, let's talk about yet another example. If you have an equation in place, so let's say we are talking about binary equations over here. And if I tell you that I have an equation a plus b plus c is equal to 15, or let's say a plus b plus c is less than 15, and I'm also trying to reimpose some constraints over there saying that a, b, and c are all greater than 4, and they have to be less than 15. And I'm saying that following these constraints, I want this equation a plus b plus c to be solved. Now, pretty sure the mathematics don't care. The mathematics doesn't care whether we are talking about bananas, we are talking about apples, we are talking about cars, we are talking about blah blah blah, whatever we are talking about. I have three quantities. I have been told they are integers. I have been given with a certain constraints, and whatever solutions I come up with, I'm pretty sure that if we are talking about apples, the solution will be applicable to apples. If we are talking about bananas, it will be applicable to bananas. So the entire abstraction behind quantum computing is that I know that there are certain physical systems out there, particularly the quantum systems, because we can leverage quantum entanglement and all these factors to increase the computation speed, and obviously the information that we can store. So if somehow I can translate a problem of logistics in terms of the equation, and I know that there is a magnetic field, there is a set of electrons, and there is a set of logic gates that are operated using quantum mechanics, and they have the same equations on the abstraction level, that I know that if I find the solution to this wave function, so whatever the solution that I'm getting, it will be applicable to this real life scenario also. So this is the first thing that I would like to cover up in this slide, that we are able to understand the abstraction between quantum computing and the real systems, the physical systems, and something as business savvy as logistics. Second, if you see the image on the right side of the slide, near-term quantum computers will be used as co-processors. So this is the comparison that I was trying to draw when I said when I tried to do the analogy of a graphical processing unit. So we have a lot of problems where let's say we are talking about training a very large language model, which we will eventually discuss in the conversational AI section. But let's say we are trying to discuss about one of these models and we want to train it. We now it's like no secret that how GPUs help us to train a lot, like huge deep learning models. But we know that there is only a certain aspect that we want to do in GPUs. It's not that we start doing 2 plus 2 on a GPU. We don't want to do that, right? We have special purposes for that. Similarly, in quantum computing, we know that when we are trying to solve that problem which rises exponentially, I'm preserving whatever resources that I'm having only for that case, and only for that case. I'm not there to say that I'm going to stream videos using a quantum computing. I'm not saying that we are there to make calculators using quantum computing. That's illogical, and that's like a total failure of of logic, I must say. So in near term, due to hardware constraints, quantum computers will be used as co-processors. So they will just be there to assist the algorithms that we are trying to solve on classical computers. Now, the question, how do we access it? Now, every other day, you'll find that one of your friends is posting that somehow I was able to get a GPU, RTX 3090 on discount. And you'll find that a very cool CPU orientation with blue lights, blue RGB lights out there. But the problem with quantum computers is that you cannot bring one home, right? Depending on the approach that a lot of companies are taking. So basically, majorly, if you look at how global companies have approached quantum computing, there are 4 or 5 approaches. You can use photons, you can use quantum gates, you can use annealing based approaches. So on the basis of that, you have these large, very large quantum computers which are stored in cryogenic sections. So basically, you have to maintain a temperature of 15 millikelvins. I'm pretty sure you don't have a fridge that big or a fridge that strong in your home that can also store chicken nuggets and as well as provide you with a temperature of 50 millikelvin at your home. So the only solution is that you try to use the solutions via the cloud services. You can access on AWS. As I mentioned, AWS bracket is there. They have put up various examples, free notebooks out there. Similarly, D-Wave Leap is one of the platforms that I have explored a lot. So you can go there. I'll make sure that I'll after the session is over, I'll share all the links, all the links that we'll be discussing on the slide, so that you can go and access all them. So yeah, this is how you can access all the cloud resources. Now again, another important point I'd like to classify that there quantum computing, since it's a buzzword out there, a lot of media articles they are trying to utilize it to gain some traction on their websites. So what happens is there is certain result that comes up in the research paper. Let's say there is a certain article on Nature where they have claimed, you can see on the screen that they have claimed that we have done the prime factorization of the number 21, that n is not the number of bits, so it's almost laughable, but it's n is equal to 21, and they had tried to do the prime factorization of that number. As I said in the second or third slide, that a lot of encryption algorithms are based on the fact that it's very difficult to find the prime factorization of large numbers. So they have demonstrated on a photonic quantum system the prime factorization of n is equal to 21, and you'll see that by the time this information is getting translated to the some media article, you will find that headlines like, are you ready for the quantum computing revolution that will break the internet and all the banking encryptions? Is it high time that governments should be scared enough of quantum computing? And what has actually happened is the prime factorization of n is equal to 21. And this is what it's very scary. Another one you can see about on climate change, one of the reports that I was reading, that quantum computers are suited to modeling complex system, making the better at forecasting both near-term weather patterns and long-term effects of climate change. Now I don't know where this research paper is, where did they got the information, and I'm also not aware that why do you need quantum computers to forecast weather. So you should be very wary of what resources that you're trying to use. And I'll say that only rely on the official pages of the programming languages that you're using, or some very reputed A-class scientific journal. The resource advantage I'd like to talk about now. If you're reading something about gravity, Newtonian classical mechanics, if you're reading about gravity, unfortunately you cannot ping Newton and call him on a Zoom call and say that I want to understand few things about what you were thinking back then. But the advantage that we have in quantum computing and artificial intelligence is that if you try well enough, you can find resources directly from the people who have invented the algorithm. So Shor's algorithm is one of the algorithms that started the I'd say the fire in quantum computing, and there are a lot of videos you will find where Shor himself is talking about what his algorithm can do. So what it does is, see, you're getting the first hand interpretation of what the algorithm is from the person that has developed it, and there is no ifs and buts involved. If the person is saying that I am the maker of the algorithm and I know that this is the limitation of the algorithm, you're sure that there's no way this person can go wrong. So this is one of the beauty of quantum computing that I'm finding, is that although it's very technical, I mean the skill gap is very high. I should say that a few years back when I was starting with AI, I remember that that you need to brush up some of the mathematics, but I very vividly remember that even today, that if I have to read about some transformer model, all I need to understand is some sort of backpropagation, some sort of embedding vectors, and it's basically something that I can revise by studying some calculus resources. I need to understand what backpropagation is, but eventually we are in a time where everything is done by wrapper functions, right? So if you're making a very simple artificial neural network, you're not doing backpropagation from scratch. You're having TensorFlow wrapper functions, you're having PyTorch wrapper functions that do the model.fit and model.predict for you. But eventually, even if you try to understand what's happening down the hood, it's very, I'd say, not very trivial. I'm saying that the mathematics involved is good if you are trying to go into some research field. But when I was looking at quantum computing and I was trying to understand that how are we trying to utilize something as complicated as a quantum mechanical system to an artificial intelligence problem, I found the skill gap to be very high, because you need to be wary of some part of physics as well as some part of AI to understand that how do you need to code out the solutions for the same. So I think because as I mentioned that we saw few of the cases where we just saw an outline of how quantum computing can help. But as I said, that we will be looking at one problem statement where the you will understand that how optimization is very easily running into one of the most difficult problems out there. So this problem is on the GitHub. I'll share the link, as I've said. All the resources that I'm using, I'll be sharing the link. But the problem statement was placement of charging stations. Okay, so let's say you are working in a startup which is responsible for placing uh, electronic vehicles charging stations. So electronic vehicles have taken the market by storm, and now since the sales have been increasing, you have been assigned with the problem that I have n number of charging stations in the city. So because I'm someone who's coming from Bangalore, so let's say the uh, charger locations that you're looking at stands for a large area of Bangalore, and you can see that the points, uh, the red points on the left image, which you can see this one, this red point, this red point. So the four red points are trying to depict the current electronic vehicles that are present in the city. And your problem is to your company stakeholders have told you that we want to put two new electronic vehicle charging stations, and what is the most optimum location where we should place them. So what mathematical constraints should we consider when we're trying to solve such a problem? Now if you look at a very brief like scenario what we are looking at, you'll see that these four constraints are something that are very important that we need to solve. I mean, obviously, if you want to add in more constraints, hats off to you. If you can think of that, it's extremely brilliant. But you need to understand that whenever you're trying to put in new electronic vehicle stations, those charging stations, these four constraints are the most major ones, the major ones. So minimizing distance to points of interests. So let's say your stakeholders have told you that I know that there are two very big shopping malls in Bangalore, which are a center of attraction on weekends, and I want that these the new electronic vehicle stations, whatever wherever you're deciding to place it, should be close to them. Okay, so the first mathematical constraint came in. The second mathematical constraint is maximize distance to existing charging stations. So as you saw in the image that you already have four charging stations, so you won't want to put a new charging station that is already like within 200 meters of either one, right? It will be just a waste of resources out there. The third constraint is maximize distance to new other charging stations. So you also have to make sure that these new stations are not very close. Again, a mathematical constraint. So similarly, you see that if you keep on adding, because this is just a demo that they have given on their GitHub repository, you'll soon find that finding the solution is almost impractical on a classical computer. And even if it's possible, it will take weeks or let's say months to run on a very large computer instance. So this is one of the problem that I wanted to, just so that you're intrigued in how quantum computing work. And as I said, that it's very difficult to show the solution because I need to go up through all the physics resources and how I'm trying to put these problems in a physical electronic system. But I'm pretty sure that if you're interested, you'll go through these articles and you can connect with me on LinkedIn, any other resource, and I'm pretty sure be there to help you. Now, since we have seen all these use cases from optimization, now let's try to link it. Now let's get to the second part of linking ML optimization problems. So I just said that quantum computing helps in optimizing a lot of helps in optimization problems. And what is machine learning? I mean, a lot of algorithms is just basically what they have is a cost function, right? You have a cost function, you have data, and what you need to do is just fit your data so that the cost function is minimized, right? There are always memes floating on social media networks is machine learning and all these stuff is just statistics. I mean, not always, but just to talk about those memes. Similarly, you can say that if you're talking about a lot of optimization problems, quantum computing can help. So there are companies like PayPal. Okay, so I read one of the use cases that PayPal had tried to delve. Obviously, this was before the recession times. Yeah, I think the problem was feature selection. Okay, so if you're looking at a transaction, and because PayPal is a company which provides with transaction services, the data that they have is high dimensional. So, from what I remember, that they were having per transaction, they were having 10,000 rows, right? So they have 10,000 rows for every transaction, and they have millions of transactions happening every day. Now, this is just raw data, right? There's nothing related to machine learning. They're just saying that I have data and I have huge amounts of them, and I am also the data that I'm having is very high dimensional. So I don't know which features out of all these 10,000 columns are important to me, right? For creating a model for, let's say, I want to do fraud detection. Fraud detection is a very common use case in finance machine learning. So let's say you are a data scientist at PayPal and you have these tons and tons of columns and tons of rows of data, and you want to find out which columns uh, should I use for creating a model out from them. Now, if you're trying to look at the number of permutations and combinations that come up, if you're trying to experiment with model building by considering that in a subset of features, either a feature is there or not. So how many it will be? It will be for every feature you have two options, right? Either it can be in the subset or either it cannot be in the subset. So you have 2 to the power 10,000 possibilities that you have to test. And for every configuration of data set that you are making, you have to train a model on that, and then you're seeing the results and you're trying to compare the results. So they partnered up with D-Wave and they tried to solve this problem by solving the QBO. Basically, QBO is quadratic unconstrained binary optimization, right? This problem is, and again, I'll just show you. So basically, in mathematics, there are problems where you want to minimize a certain expression, and the particular cases where x, all the x values, so x1, x2, x3, x4, all these values are binary. So and you are either trying to put constraints on them, like I mentioned that a plus b plus c have to be equal to 15, and a, b, and c in individual values cannot be less than 1. Okay, so if you're trying to put in some constraints, so or if you're trying to put solve these equations without any constraints, so that is why they're known as quadratic unconstrained binary optimization. Binary because, as I said in logistics, what you can do is that you can select that you want to uh, put a shipment from either using a truck or either using a ship. So it might be difficult to grasp in one single session, but I think I'm able to connect the dots that how this optimization of cost function or a sub part of the AI problem, it can be leveraged when you're using quantum computing, right? So I'll definitely share the resources, all these resources where once you are a bit comfortable with what quantum mechanics is, then I think you can delve in. Directly delving into these resources won't help a lot because uh, these graphical images might be very good to read. The language might be very good to read, but as soon as some logical diagrams come up, some mathematics come up, you'll be confused at what's happening over here. So I'll definitely share all the resources over there. So now, once we are done with the quantum computing part and trying to link it, what sort of ways that it can help in artificial intelligence. Now I'll come up to the second part, right? That is problems faced in conversational AI. So as I said that over the last 1 year, I have been working on a lot of conversational AI problems, and I have seen that during the time where I was just preparing for interviews and reading these from a more theoretical standpoint, I saw that a lot of problems come up once we are starting dealing with the customers. The customers can be your clients, or obviously the people who you're trying to deal with once the model is deployed. Okay, so we will be talking about these 5 sections. The first one is open-ended problems and lack of data. The second one is native language issues, which you'll understand once we get to the slide. The third one is production costs, machine learning operations. After that, we have problems with generative models and how to detect model performance in real time. So, without wasting any time, let's get started. So, often you might find situations, you might find yourself in a situation where you don't have a very classical data set with you. Not everything is a classical Kaggle data set that you're having. So, if you are working, let's say, in an analytics firm out there, which is very new to AI, who has never ever worked with AI, and they are trying to look at their competitors, and they are seeing that their competitors are getting results. They have increased their revenue by let's say twofolds or threefolds the moment that they incorporated AI, or it might be they have taken out the human in the loop and they have cut their costs. So often it happens that if you're working in some sort of analytics firm, some consulting firms, clients come up with very open-ended system questions that we want to explore AI. Just tell us how can AI help us, and then you, as people who are working as data scientists or whatever your designation might be, but it's your responsibility to ask intelligent questions. Even though you are aware of all the algorithms out there, even if you are aware of how big data works and how all these complicated algorithms work, the first question that should come up is it's so open ended that almost you need to ask very intelligent questions in order to narrow down all the possibilities. Now, let's say they are talking about we want to automate the XYZ process, like they have a process of document verification. They want to automate it. They don't come up with what data that they are having. You need to ask them questions. Okay, so you should be prepared not only with something like SQL, like people say that, or some big data tools that you should be able to extract data once you are given data. You should always try to equip yourself with understanding that without context, if you're asked that okay, I am working in so and so domain, I am a client who is working in grocery sector, and I'm coming up to you and I'm asking that is a potential client, and I'm asking that the client is asking you that I have this data, I don't know what to do with it, but somehow I want to leverage AI and I want to do some chatbot. I don't know what to do with it, but You should be the one who should be understanding and asking intelligent questions. So this is one of the biggest problems that I face, that sometimes the conversation starts with completely blank and open-ended question, right? The second, I was in a conversation with one of the leading e-commerce websites. I was the conversation with their engineering team, particularly the deep learning team, and I was talking about the search feature, right? So this is a very prominent use case where you'll understand that suddenly all your work can go in vain because you have failed to understand the customer, right? So let's say you are building a recommendation system, and what you're trying to do is a customer came up to you, depending on what his or her interests are, and the customer is trying to find out, let's say, a piece of clothing. Now, the first thing that this big e-commerce uh, company had to uh, uh, understand was the market audience, or let's say the audience, the target customer in India might be coming from rural areas, right? Suburban areas, which is not very educated when it comes to the traditional education sector. But now everybody is owning a smartphone. So let's say a user comes up and he or she is excited that I have heard the word jeans. I'm not very educated, but I'm typing JINS, jeans, right? Similarly, let's say someone from uh, the northern area of India is not very educated, but uh, the person is trying to write JUTE. So obviously, because you have trained your recommendation system on English language tokens, it will read it as jute, sorry, jute. But the person might be referencing to jute. You often do Hindi and English searches together, right? Because you cannot assume that your customer. It's not that hard uh, instruction on Flipkart that dare you use English language on the search panel over here. Similarly, if you're talking about even someone who is very tech savvy, but let's imagine for this case scenario that Nike was not a famous company, and you heard it for the first time, and 6 months later you're trying to type it on your e-commerce platform. That I remember hearing something 6 months back from my friends. I don't remember what is nuke, was it Nike, what it was. So you just wrote nuke. So your system should be intelligent enough to recognize the spelling mistake and give you suggestions that okay, the user might be talking about Nike. So you see that grammar mistakes, spelling mistakes, often you'll find out that the way you chat on your WhatsApp is not the same as what you write in your exams during your English exams, right? You don't care about grammar. You don't write I want to, you write I wanna. So you use slangs, you use shortcuts. The spelling of great might be GR8, right? So you need to understand that what customer base you are talking to. Now, if you're building a bot for Discord, right? If you're building an AI bot for Discord, and you cannot take the assumption that everybody who's going to come up to stream their games, or let's say whatever they're streaming on Twitch or something, that they're going to follow strict Shakespearean grammatical rules. Okay, so this is one of the important problems that we face in conversational AI, and again, we can have an entire session on how the solution is, what the solution is. But uh, if somebody is having queries and they are interested, they can contact me through LinkedIn. The next is holding conversations more than just classifying intents. Holding conversations. Now, by the time I was making this presentation, I was remembering my conversations with GPT, right? And I had one interaction with one of the people who was trying to try to uh, attach a chatbot with his banking application. Now, it's very difficult for chatbots to hold conversations, right? To remember the context, like 6 lines after the initial message, is it remembering what I talked with it? And this is one of the problems with large language models. We will discuss it in the next slide, as you've already seen in the contents page. So you see, holding a conversation is something that's so important when the matter is very crucial, like in healthcare sector, like in finance sector. You don't want to just like frustrate your customers, because any procedure that if you're talking to a banking chatbot, it's not that you want to go and question that, hey dude, how are you, and okay, okay, bye bye. You want some results from that. I mean, people might have worked with Lex bots, Google Dialogflow, but eventually I have seen that even in production, the if you look at the success rate, nobody will tell you that okay, the results were 100% satisfactory. Not only with chatbots, or it's almost with any AI model out there, right? Now we come with to the point of production costs and machine learning operations. So 5 years back, the main agenda was to convince organizations that you should use AI, you should use AI. See, this is what AI can do for you. Today, a lot of organizations, you might end up working in an organization that is already doing a lot of AI work, and straight away you might need to head up to the part of ML operations. That is, hey, I have 6 models running in my environment. I need you to understand that how much do I need to retrain, what interval I need to retrain, and where should I redeploy it? Should I use EC2 instances? Should I make serverless AWS SageMaker endpoints? So you see, this is machine learning operations tool. It's becoming so important these days. You will find that there are a lot of organizations particularly dedicated for making tools for machine learning operations, so that someone who has having no knowledge of AI, mathematical knowledge of AI, what they can do is that they can input their data from some UI application, train their model from some UI application, and then deploy the model using some clicks. So you see, because now a lot of companies have already adopted AI. So now, if you say that if you're a college student, like yeah, if you're someone who is a college student and attending this session, if you're saying that I know statistics, I know bag of words model, I know how glove vectors work, and I know how to make a model and fine tune a BERT, that's not going to help. Okay, because eventually, if someone you're competing with knows how to deploy those models, optimize those endpoints, and obviously that person, then obviously that person will have an edge over you. So you need to know how to make RESTful APIs from the models that you have trained. You need to justify that if it's interpretable. Okay, why is it interpretable? Where am I getting wrong if I'm getting wrong results? And again, if your inference part is wrong, if say my I have deployed a chatbot in a banking sector, if my customer is not getting the desired response, then what? Because this is one of the most important aspects when you are working in a ROI focused, return on investment focused industry. That I don't care you're using a Rubik's cube, you're using a quantum computer, you're using AI, or you're using some Dishitra algorithm. I don't care what you're using. My customer should be satisfied, and that should be the goal of any. If you're not interested, I'm again making it very clear. If you're trying to, as a student, if you're trying to pursue masters or your interest is completely academical, then your goal should be completely different. It should be like getting 1% increase in the accuracy. It's a very big feat for you. If you're trying to make state of the art algorithms, that's good for you. But if you're working in an organization where results are more important than what algorithm you are using, nobody is going to tell you to replace their simple calculator by AI because uh, a new AI, a very cool or tech savvy AI has been found. They'll just say, why the hell am I paying for a calculator using AI? That's a free application in my phone. So it's very important that how do you decipher, how often do you need to retrain the models, how do you detect that, because you're not getting any ground truth from inferencing results, right? Once you have deployed the model, it's not that you are splitting data and train and test, right? You're not getting ground truth. You have to put some human in the label. So again, another problem is hyperparameter tuning. I remember when I was doing projects on my Jupyter notebooks, it's very easy, like do grid search CV, put as many values you want. But now let's say you're doing it in a client environment and the cloud environment is charging you for it. So how do you optimize? Do you make some intelligent guesses? So how do you do that? So again, for that, for understanding the data drift part, I will provide this link. This is one of the services where this is a blog by an AWS machine learning engineer itself. That how do you detect data drift using custom Amazon SageMaker model monitor? So they have a service of model monitoring, where what they do is that once you have trained a model and you have deployed it using a SageMaker endpoint, then how in production you can, after fine tuning the BERT, you can compare the change in distribution, incoming distribution. So I'm pretty sure if someone has read some statistics, they are aware of how to compare two distributions. Like KL divergence is something that is coming to my mind. One of the most simple algorithms out there. So similarly, there are a lot of ways. This particular blog is about covariance shift, how the embeddings, the distribution of the embeddings are shifting, right? So I'll highly encourage you to go through this. It will help you understand that the actual problem starts once you have deployed the models, because almost everything is being automated. You have SageMaker, you have all these models that you can just call, these images you can just call on SageMaker, and the training will start. But to save the cost once the model has been deployed, understanding that how often the periodicity of my customer changes, right? Like if you're trying to do weather prediction using some AI model, then what should be your frequency? It should be like 2 3 days, right? If you'll do weather predictions every 6 months, then I think your application is doomed, right? So I'll share this resources once again, and if anybody is having some issues, they can eventually connect with me. Now let's talk about the fourth aspect, that is problems with generative models. Now, you might have heard about GPT, right? Now, how it is different from the earlier tasks. Earlier, we were talking about classification problems, named entity recognition problems, right? Where we are trying to just find whether what is the sentiment classification problem. The classical Kaggle problems are college level projects that we used to talk about, right? Now, let's say, not only in the case of conversational AI, if we talk about computer vision, we have the stable diffusion, we have mid journey, right? You see these AI models and you say that, okay, wow, what has AI become? GPT is like something that is creating text out there. But again, the problem is that these generative models, I'm not talking about the images one. Images one has taken the world by storm, and it's there. It's a completely different use case. NLP and computer vision are different use cases. Always keep this in mind. Now, what is the problem with generative text models? They are unpredictable. Now, I've taken this thing, this image that you're seeing on the right, directly from their official page. So it's not that some third-party review that I'm giving. It's directly from their official page, ChatGPT. ChatGPT was published in this year's Neuro IPS conference. So the limitations are may occasionally generate incorrect information. Now, I was obviously I have tried to test it with a very weird example, I'd say. So I tried to test it and I asked, when did Tom Cruise marry Queen Elizabeth? And to my surprise, because I wasn't expecting the chat GPT to give me answers which are factually correct. I mean, you can obviously break the algorithm and get wrong information, but two things are important. As we are gradually increasing in terms of technology, you can see that it has able to understand that my question was wrong, that it has never happened in reality. And the second very important thing, like I mentioned, that it's very difficult to maintain conversations, right? And why is it very difficult? Because we as humans, when I ask you as a human that when did Tom Cruise marry Queen Elizabeth, and you tell me that, dude, what rubbish you're talking, it has never happened. And then I put this question again, that whom did he marry? It's easy for you to understand that I'm talking about Tom Cruise, but for AI, for an AI model to understand that the whom stands for Tom Cruise, and then answer accordingly that yes. And again, I reiterated that, are you sure about that? And again, I got the correct answer. So I have not tinkered a lot because, as I said, Neuro IPS 2022 was a few days back, and ChatGPT has been published recently. But if you look at the older versions of GPT, you'll find that the factual correctness is one of the big problems in text generation. So you cannot leave these models unsupervised. This is a very, very, very crucial thing that you need to understand. You cannot leave these models unsupervised as of now. So how do you make money out of this, or how do you pitch it to the clients? The one of the problem possible solutions is that you pitch this thing not as something that would replace human beings, rather assist them. So I'll give you a scenario. On one side, I'm telling you that I have an AI which will write 300 essays for you, right? Unsupervised. That is something wrong, because this AI might make factual mistakes. It might go wrong. It can make huge blunders. But if I tell you, and this is how I pitch to someone who I want to sell GPT, that hey, what is easier, writing 300 essays or reviewing 300 essays? Then obviously the person will say that obviously reading as 300 essays is easier, right? Instead of writing it from your brain, thinking about what I should write next. So this is how I think in near term these generative models would be sold out there. That it's not there to be left unsupervised, but what I'll do is that I'll assist you in writing, and what I have done for you is that I have taken the work of writing essays for you, writing emails for you, writing documentations for you, scripts for you, and now only thing you have to do is maybe look review the essays and maybe look for minor grammatical, minor factual mistakes, right? So the last thing in today's session we'll be discussing about is the inferencing cost. Now these models are huge. Now if you're talking about GPTs, or even if you're talking about large language models like GPTs, then you'll find that these models are huge. This is not an sklearn logistic regression models with few weights. So how do you put it in production? Again, this is a very complicated topic, but I need you to understand that tomorrow, if you're trying to integrate some large language models, because it will happen, trust me, it will happen. Text generation use case, summarization use case, if you the moment you are stepping into this and your manager, or let's say any person here, is asking you that, hey, what are your plans for deploying this, because I know that the size of the model is huge, I might face latency issues, I might face inferencing costs. uh, like I want to inference a large language model, am I doing it on the CPU or do I do it on a GPU? So on the right left side, you see that one of the services that NVIDIA provides, NVIDIA Triton, which helps in scaling up the inferences of large models by accelerating using a lot of parallel GPUs, multi-node inferences. And on the right side, I have taken a pic from one of the blogs, and again, I'll reference the blog. This is high performance inferencing with transformer models in Spark, where what you do is you are using parallel inferencing. So I want you to focus on this line, that weight that is more. Despite costing 5 to 20 times a CPU instance, inferencing done by a GPU instance can actually be more cost effective because it is done 30 to 100 times faster, depending on what configuration of GPU you have selected on your cloud resources. So I think with this, I think what we should do is we should. I've already discussed how to detect model performance in real time when I went to the SageMaker page. So with this, I think we should just do a recap of what today we have discussed and what should be the key takeaways. We started with quantum computing. We went into the philosophical aspect of what are the limitations that classical computers uh, have, and where quantum computers jump in. Once this was done, we tried to follow up with few of the real life applications. I try to make sure that you are trying to understand or trying to gain interest in what subgenre of problems quantum computer can help solve. I think you also respect the fact that quantum computers are just here to assist and not to replace. And this is, I think, very important for us to understand that in near term, it's very difficult to make solutions that are on a production scale. And hence, we need to understand that we are not falling prey to uh, unsolicited, unfaithful hype out there, and we try to follow as much as the good resources that which we can rely on. So this was about quantum computing. Then we try to link up that we have a lot of optimization problems within machine learning also. So definitely in near term and in current scenarios also, there are a lot of applications, algorithms which you can go and study once you have your basics of quantum computing, very little, like very basic quantum computation clear. Then we went to the part of conversational AI. Again, drawing an analogy, conversational AI is something that is being now well adopted, but there are challenges that exist even today. And we discussed five, we try to divide these challenges into five subdivisions, and we discussed the first one was open-ended problems, lack of data, and sometimes more data, having more data where you have to ask intelligent questions that, hey, I don't need all this gibberish data, only this much is enough for me. Then we talked about how you need to understand your audience, which is very important because ultimately you are trying to get some return on your entire investments. If you are working as a data scientist and eventually, god forbid, that your manager notices that whatever solution that we are trying to put up in front of the customer, my revenues are not increasing, or this entire services that have been costing me pennies, huge amounts of monies on cloud services are not giving results, then what is the very need to keep it? Let's discard the entire program. Then we went to the field of machine learning operations, how the adoption of AI has changed the shift from just getting in the data to an entire different aspect where these problems have become rather sometimes easier, and we are focused on redeploying, monitoring, inferencing aspects more, and retraining. We talked about chat gpt, we talked about generative models, the problems with them, and how I think the near term solution would be to resell or sell them in a way that they are assisting you and they are not replacing you. And with this, we come to an end of the session. I will stop sharing. Eventually, you can connect with me on LinkedIn if you have some queries.
Yeah. Thanks, Siddharth, for the awesome session covering a lot of topics. I would say because this was important to understand not only machine learning aspect, because in our previous sessions we have been going deeper into machine learning as such, going into the very core tech of data science and all those stuffs. But combining all these stuffs and how these things matter and how these things really fit in place, moving ahead really is useful for the community members. And thanks for that. Thanks for taking time and to taking us through this combination of all these topics. And we have a few questions because we
Sure.
are over on time. I'm trying to pick up two questions from the community members that they have sent to us. So first is like we know about the power of quantum computing, and definitely we
Mhm.
got to know more about from the session that you took. But it's like if someone wants to get started, they think because still there is a hype that quantum computing is something which requires a lot of knowledge around computation, a lot of knowledge around mathematics or something like that, right? Like a lot of theoretical knowledge, all those stuff.
Mhm.
Similarly, machine learning also has that. People starting machine learning also have that thing that they need to be very strong on linear algebra, statistics, probability. So if they want to fuse it, and definitely the industry is using the opportunities to get revenue or to get certain benefits out of the combination, right? So how should they start? Like if someone is starting, like let's say if someone is in their third year, or in, like let's say
Mhm.
a student is trying to enter the industry and is quite fascinated about how they can fuse quantum computing, machine learning and all those stuffs to get into a place where actually industry demands their skill sets, right? So how would you
Mhm.
suggest and what have been your journey around that?
Yep, yep. So I'd suggest that when you are beginning with machine learning and quantum computing, so as you said, that the guy or the person is in third year, then when the person is starting, I think the person should keep these two fields very distinct,
Hmm.
and then read them without trying to connect the dots.
Perfect.
Like, because
Yes.
it's very important to understand that, let's say, when you were in your high school, you were reading calculus, right?
Hmm.
At that time, did you know that one day you'll use this for backpropagation? And the beauty was that uh, you dedicated your entire time to solve calculus problems, integration calculus problems. And I think because the fact that you were entirely focused on that helped you a lot when you were gaining, when you're trying to start deep learning, right? You thought, oh, backpropagation, chain rule, I know this. It's very easy. So quantum computing is something that again requires a different set of theoretical aspect. So eventually, I'd say that start differently. Don't try to mix it. And once you'll see that the moment when you get to an aspect, the time where you have to fuse them, you'll see that it's very trivial.
Hmm.
Because you have a very good understanding of machine learning also, and you have a very good understanding of uh, quantum computing also.
Yes. So that matters because the core lies that your basics should be clear around any domain that you're trying to get into.
Yeah.
Because this thing really matters that you are not aware of the basics and then you are trying to fuse two topics together and then you will mess the things up badly. So like that,
Yeah.
that's a very genuine and very useful insight around the domain. And so second stuff would be it's like we have seen machine learning applications going across a lot of industries, like be it pharma, be it financial organizations or all those stuffs. And so like could you talk could you think of like, because the more data they are generating, because with time the data generation would definitely increase, and then the power of processing and all those, so definitely we have GPUs and all those faster processing things. So how do you see quantum computers and all those setups that we have trying to boost or trying to help machine learning get better and faster?
Yep. So, as I said, that there is one aspect where that we need to understand a lot is that what is the hardware state of quantum computing, right?
Hmm.
So, if you look at services like D-Wave and IBM Qiskit, so currently, I think 3-4 weeks back only, IBM Qiskit released a processor where they have 433 qubits, right?
Hmm.
So I'd just like to draw an analogy with the concept of AI winters. I mean, if you look at the courses of Andrew Ng and stuff, there you might have seen the concept of AI winters. That the theoretical parts of AI had already started in 1960s, 1950s, but the problem was that the gathering part was not there, right? And you didn't have computer resources. So the bottleneck that you can phrase it as a quantum winters is that you have a lot of data. You know that on theory, on practical, on papers, if you entangle a lot of qubits, so there is a concept of entangling the qubits so that you can use the superposition to calculate the problems. I'll just give one very simple mathematical example. If you have an unstructured database and you have to perform a query out of that, then
Hmm.
the worst complexity that you can have is n, like in n time. You have n entries, and because there is no structure in there, you cannot apply some binary search or any other algorithm. So the time complexity in worst case scenario goes to n. But if you're looking at solving the same problem using superposition qubits, the time complexity reduces to root n. I mean, this will again be counter your
Hmm.
common
Hmm.
sense that how is this possible? But again,
Hmm.
the fact arises from the fact that on the computation level they have these qubits in an entangled state. So you might have seen that these qubits will have, in a layman term, the same wave function. So if you're taking the calculation of one of them, you are basically reading the results on a bunch of other qubits also. So it's like you are reading it in one place, but you're getting the results from subsequent other place. This is in a
Hmm.
very
Hmm.
layman
Hmm.
language, not mathematical, but you understand that what's happening over there. Now the problem is there, the problem that exists, it's difficult to keep these qubits in entangled state. That is the hardware restriction that we are having right now. So on theory, you can say that I have a big data set, I have a machine learning problem, and I have 600 qubits that are entangled, and you have the
Hmm.
solution. Voila, you get it. The
Hmm.
physical problem is that much only, that it's now difficult to maintain those qubits in entangled state. They leave out even if you get one photon or any small disturbance,
Yes.
so that
Yes.
the decoherence breaks. They become decoherent. That is the only problem. So, and all these companies, these hardware companies, they are trying to solve this. Eventually,
Hmm.
in some decades, uh, there are business problems which are not that scalable, but they are there. But you need to study for that. Obviously, it's
Yes.
difficult to cover in one session.
Yes. So thank you so much, Siddharth, for covering this up. And to the attendees, we would be sharing the links and all the resources that Siddharth has used. So stay tuned and thanks for joining and stay safe. Bye bye.